Now focal length of a lens when medium on both sides of lens is not same. See, if this is a lens, suppose on this side medium has a refractive index mu1, lens material has refractive index mu2, and this side has a refractive index mu3. Then what is focal length for this lens? So it is given by mu3 upon V minus mu1 upon U is equal to mu2 minus mu1 upon R1 plus mu3 minus mu2 upon R2. Now if object is kept at infinity, then U becomes infinity and V is said to be focal length. So if object is at infinity, that is U is equal to infinity, then V is equal to focal length. This we know, so replace it. So it is mu3 upon focus is equal to, this becomes 0, mu2 minus mu1 upon R1 plus mu3 minus mu2 upon R2. So if you want to find focal length, that is 1 upon f, you have to move mu3 on this side and then you have to simplify it. So I can write it like this also, 1 upon f is 1 upon mu3 whole multiplied by mu2 minus mu1 upon R1 plus mu3 minus mu2 upon R2. So remember this formula. This is going to use if on both sides medium is different. If object and image distances are measured from focus. Suppose this is convex lens, this is first focus f1, this is second focus f2, this distance is f2 second focal length and this distance is f1 first focal length. This is optical center O. Now if I take object somewhere here at distance x1 from f1 and suppose image is formed somewhere here at distance x2 from f2, then what is the relation between f1, f2, x1, x2 that we want to find? So here object distance u, numerical value can be taken as f1 plus x1, while image distance v can be taken as f2 plus x2. Now applying lens formula, 1 upon v minus 1 upon u is 1 upon f. Suppose first and second principle if I take it, f1 and f2 are equal to f when medium on both sides is same. So I'm taking medium on both sides same. So here f1 f2 both are equal, so we can write at place of f1 or f2 equal to f, and here too it is f. Now simplify this. This is 1 upon f plus x2 plus 1 upon f plus x1 is equal to 1 upon f. So it is f plus x1 plus f plus x2 upon f x2 f x1 equal to 1 upon f. So if I cross multiply this, this is f square plus fx1 plus fx2 plus x1 x2 is equal to this into this, f square plus f x1 plus f square plus f x2. fx2 cancel, f1 fx1 cancel, this cancel, so what is left? x1 x2 is equal to f square, so f is equal to under root x1 x2. So this is focal length of lens, and this is called Newton's formula. Now deviation produced by lens. Lens is used to produce deviation in the light. So let us see how deviation will be produced, how much deviation will be produced by lens. Suppose this is object. If a ray is incident on lens at this position, at height h from optical center, and it bends light towards principal axis, so image is formed somewhere here. This was the original direction, so this lens has deviated light by this much angle. Let it be delta. Suppose this angle is alpha, this angle is beta. Let this point be M. So here you got a triangle. Let this point be C. O I M. In triangle OIM, these two angles are interior opposite angle of this, so sum of these two angles should be equal to this. This is property of triangle, you know, so we can write delta is equal to alpha plus beta, and these angles are small. Here point M is very near to C, so that H is very small. Hence angles will be small, so we can take this as tan delta equal to tan alpha plus tan beta. So we can write it tan delta is equal to tan alpha plus tan beta, or tan alpha is this divided by this, tan beta is this divided by this. So we can write this as h divided by this distance, and it is object distance but measured in this direction, so it is minus u. So minus u plus tan beta h divided by v is positive. So if I take h common, then it is 1 upon v minus 1 upon u is equal to tan delta. Now we know this 1 upon v minus 1 upon u is 1 upon f, so it is h divided by f. And as you know, angles are small, so at place of tan delta we can write only delta. So deviation produced by lens is given by this formula, but this is valid only if h is small or alpha beta angles are small. So valid for small h. Now more is the focal length, lesser is the deviation. Lesser is the focal length, more is the deviation. So deviation in light produced by lens is inversely proportional to focal length, but deviation produced by lens is directly proportional to its power. So here if I say power of lens it measures ability of lens, it is a measure of ability of lens to bend light. If lens bend more or bending of light is more by lens, then we say power of lens is more. So power is directly proportional to amount of bending or amount of deviation, and that is directly proportional to 1 upon focal length. So here power is defined like this: 1 upon focal length. Proportionality constant is taken to be 1. So power of lens is defined like this. More is the power, more is deviation produced by lens, but if power is more, focal length will be lesser. If power is lesser, focal length will be more. So if lens has got more focal length, it will produce less bending. If lens has got lesser focal length, it will produce more bending because its power will be more. Now unit of power is diopter, but here focal length should be in meter. Unit of power is diopter, and focal length must be kept in meter. Focal length must be in meter unit. This is white light. Then you know different color has got different focal length, because 1 upon focal length is mu minus 1 1 upon r1 minus 1 upon r2. If equiconvex lens, then focal length is this. It means more is the refractive index, lesser will be focal length. So there is some relation between focal length and refractive index of material of lens. So if refractive index, you know, is more for, because the refractive index, some constant, some other constant upon wavelength square, more is the wavelength, lesser is the refractive index. You know, red color has more wavelength, so lesser refractive index, more focal length. So if focal length is more, it going to bend light at larger distance. If focal length is less, it going to bend light more, like this. So red color light has lesser refractive index, so more focal length. It means here you are going to see red image. So bending of red color light is lesser than bending of violet color light, and here you are going to get violet image. So if white light pass through lens, it splits into colors and it forms different color images between these 2 points. So image formed is not sharp, it becomes blurred, and this is a defect of this lens, that is called chromatic aberration. We will be seeing it later on. Here you have to remember, if a white light incident on lens, red light is bended less than violet light, because this was the original direction. This is angle of deviation for red color, and this is angle of deviation for violet color. So deviation for red color is lesser than deviation for violet color. Now next is a relation between diameter of aperture and maximum thickness of plano-convex lens. You know, suppose this is a glass sphere. If I cut this much part, so this is a plano-convex lens. This is the maximum thickness of this plano-convex lens. Suppose this sphere has a radius r, so from this point to this point is 2r. Suppose this maximum thickness is t, and from here to here it is 2r minus t. This whole is 2r minus t, because from here to here it is 2r diameter, and this is called aperture of lens, diameter of aperture of lens. Let this be y and this is also y. Then suppose the radius of curvature of this curved surface be r. Then we can write 2r minus t into t is equal to y into y, right? This distance into this distance equal to this distance into this distance. Now if you open this bracket, it is 2rt minus t square is equal to y square. Y is half of diameter of aperture. Now this is thin lens. So if lens is thin, then T will be small. So I can neglect higher power of T. So as T is small, hence T square is much small. So neglecting it, now we can write 2RT is y square. So this is a relation between radius of curvature, maximum thickness and diameter of aperture. This is half of diameter of aperture. So if you take diameter of aperture of lens as D, this is diameter of aperture, then y is D by 2. So this is relation between radius of curvature of the surface of lens, maximum thickness of lens and diameter of aperture of lens. So remember this formula. Now, let us see one example on this. Suppose diameter of aperture is 6 centimeter, that is given, and maximum thickness of plano-convex lens is 3 centimeter, that is also given. Suppose a refractive index is 3 by 2, then find focal length of plano-convex lens. Find focal length of plano-convex lens. This is plano-convex lens. So maximum thickness is this, diameter of aperture is this. These two information is given, and a refractive index of material of this plano-convex lens is also given. So how to find radius? By using this formula. It is 2 into R not known into 3 T. It is 3 millimeter. So you have to convert it into centimeter. It will be 0.3 centimeter is equal to y square. Y will be half of this. So it is 3 square. So 2R into 0.3 is equal to 9. So R will be 9 divided by 2 into 0.3, or 90 divided by 2 into 3. This is 30. So it is 15 centimeter. So R is 15 centimeter. Now F, 1 upon F mu minus 1 upon R1. R1 is R, R2 is infinity, R2 is negative also. So this becomes 0. 1 upon F is 1.5 minus 1 to 1 upon 15, right? So it is 1 upon F is equal to 0.5, that is 1 upon 2 into 1 upon 15. So F is 2 into 15, that is 30 centimeter. So this is your answer.